Hello, welcome back to the course on signal processing for music applications. In this Transformations week, we are talking about how the spectral modeling strategies that we have been presenting throughout the course can be used for transforming sounds. And in these programming lectures, we are actually trying to understand those transformations from a programming perspective by actually looking at the code of the SMS tools and trying to understand and use these transformation possibilities. So we are actually going through this block diagram. This is the block diagram of the analysis synthesis of the sinusoidal model. And what we're doing now is from the output of the sinusoidal model, by just taking the amplitude and frequencies of the sinusoid, we are applying some transformations to them and then resynthesizing the sound. And if you notice here, the phase information of the analysis is not being used. Most of the transformations require to regenerate the phases because we are changing time or we are changing the frequency, and therefore it affects the phase. So the original phases are not used anymore, and we are regenerating the phases. And first I want to look at this issue and see how relevant it is to not preserve the phases of the original sound. So I wrote this little script in which I analyze a sound, a piano sound, using the sinusoidal model, and I do analysis and synthesis. Okay, so first I have all the packages that need to be imported. Then I have all these parameters for the analysis that are needed. The window size, FFT size, etc. And then, well, I read the file, I get a window that I need, a humming window in this case, and I call the analysis function of the sinusoidal model file, okay? And it returns frequencies, magnitudes, and phases. Now I want to call the synthesis of that. In fact, let's use everything. So let's use the frequencies, the magnitudes, and the phases of the analysis, and let's generate a sound. Okay, so let's save this and let's run this file. Okay, so now it has executed everything, and let's plot first the input sound X, and we can plot on top of it the output sound Y. Okay, they're very close, and in fact if you listen to them also clearly they should be quite close. So if we just type the input sound from that, move this here, from the piano. Okay, and let's listen to that. And now we can play the resynthesized sound, so the test2.waf that I created. Okay, they're quite similar. The attacks are a little bit not ideal. But now let's zoom into one fragment of this. Okay, for example, this region here, and let's take a tiny version of it, a tiny section. So clearly they are very similar. They're not identical. Well, the blue is the original and the green is the synthesized. The synthesized has lost some aspect of it, but they look very close. They're a little bit different in the high frequencies in the contours. Okay. Now let's do the synthesis, but instead of using the original phases, let's pass an array, an empty array. And this is the condition that then the synthesis will recreate these phases, and we're going to see that next. But let's just run this. Let's run it again. Okay, let's run this file. And now we can do the same thing. We can just first plot the input sound, then we can plot the output sound already we can see that they're different. And of course we can play it. We can, for example, play the sound that was generated. Basically looks identical, then it sounds identical than the synthesized sound with faces. But if we look at the faces, if we look at the shape of the waveform, which are going to be the phase information, we zoom in into a tiny portion of it, and maybe a little bit more. Okay, clearly the shapes of the waveforms are very different. The input and output shapes are very different. That means that the phase is quite different. They all preserve a phase continuity, but the phase is different. Okay, so basically in the synthesized, now we have generated the phases. Let's go to the sine model file in where the synthesize is performed. So in the sinusoidal model synthesis here, okay, in this function, that's where it passes, it accepts the frequency, magnitude, and phases, and it calls the synthesis. Okay, and then in the main loop, we can see that there is some lines to take care of these phase issues. Basically, if the input parameter, if the T phase parameter exists, so it means that there is an array that is bigger than 0, it will use as the synthesis phase this phase. Otherwise, it generates the phase using this line. Okay, what this does is starts from an initialized phase that is initialized before here. It's initialized as random phases the first time through, and every time after that, it increments the previous phase by, let's say, the frequency, the new frequency. So it takes the frequency that has to be synthesized, and using the hop size, it computes basically the phase that the new frame should have. So it does phase continuity, but without measuring or using the analysis phases. Okay, and this is what results into this shape that we saw here. Okay, now out of these, the sinusoidal transformation, so this is the file what implements the different transformations on the sinusoidal representation, and basically there are two types, the time scaling ones and the frequency scaling ones. The time scaling is very simple, it accepts frequencies and magnitudes, so again no phase is here, and what it does is basically it creates frames in between. So the core part of this function, which is this, it keeps creating a new matrix, a new array of frequencies and magnitudes, and it adds interpolated frames in between. It actually does not interpolate, it just simply repeats or jumps actual frames. Okay, so that's the way that we can create a much longer set of frames. So the frame rate is exactly the same, and it keeps adding or deleting frames in order to make it longer or shorter the sound. And for the frequency scaling, it's simpler. It basically just takes the frequencies, okay, at every frame, and the frequency scaling can vary in time, the same thing that the time scaling was varying in time, and now it will multiply every single frequency value of all the sinusoids of a particular frame by this scaling factor at that particular frame. And that's basically all it does. Then we have the sineTransformations function that actually calls the analysis and transformation and synthesis and displays the results, and this is the file that is used from the graphical interface. So in here we have a function that performs the analysis and has some default parameters, and it does just the standard analysis that we have seen, but it plots intermediate data. And then there is this file transformation and synthesis that accepts the analysis parameters that we have obtained without the phases, and then it performs these transformations that we just mentioned, the frequency scaling from a given array of scaling factors, and then it has the time scaling that performs time scaling operations. And then, of course, it does the synthesis and it writes the file. So let's call this. Okay, so it plots two figures. It plots the figure of the analysis, in which we see the intermediate data and the resynthesized, and it plots the modified version in which the sinusoids have been scaled, both in frequency, so we see here some clear transformations, and in time, in which the duration has changed. And that's all. So basically, this was an explanation of the code of the within SMS tools that performs sinusoidal transformations. These sinusoidal transformations can be quite powerful because we have quite a bit of flexibility, and we can do some interesting time stretching and frequency shifting or transposition operations that sound very nice. So next lecture we will continue in presenting the possibilities of another transformation and another model. In this case, it's going to be the harmonic plus stochastic model, and we'll be talking about the morphing that we already have seen in the demonstrations, but we're actually going to try to understand the code of it. So thank you very much, and I see you next class.